Welcome to Wisdom Docs. Tonight, before you let the day fall away from you, I want to tell you about two mountain ranges that are, in truth, only one. And I want to tell it slowly because there is no hurry here, none at all. You do not have to follow every word. You do not have to remember any of it. You only have to let it carry you the way a slow current carries a leaf, gently, with no particular destination in mind until the room around you softens and the weight behind your eyes grows heavy and kind. So, let us begin somewhere far away. Let us begin in the Scottish Highlands. Picture them if you like, though you do not have to, the long backs of the hills, worn down and rounded over, dressed in their browns and faded greens, the heather pressed flat by wind, the rock showing through in grey shoulders where the soil has slipped away. There is a particular quietness to those mountains. They are not jagged, they are not sharp, they do not knife up into the sky the way the young mountains of the world do. They roll, they lean, they have the softened look of something very, very old, like the face of an elder, like a stone that has been held in the hand and turned over for a long, long time. To walk among them is to feel that they have always been there and always will be. They feel permanent. They feel like the very definition of the word. Now I want you to do something gentle in your mind. I want you to lift up out of those highlands slowly, the way you might rise in a dream, without effort, without sound, up over the grey lochs and the long glens, up over the coast where the land gives way to the cold North Atlantic. And then I want you to carry yourself west, across the whole grey breadth of that ocean, 3,000 miles of open water and slow waves until the land rises again on the far side. Until you are standing, in your mind, in the forests of North Carolina, in the southern reaches of the Appalachian Mountains. And here too, the mountains are old. Here too, they are soft and rounded and dressed in green, blanketed in trees, layered in that famous blue haze that gives the Blue Ridge its name. The ridges run on and on toward the horizon, fold after fold, gentle and worn and patient. They do not knife into the sky either. They lean and they roll exactly the way the highlands lean and roll. And if you have ever stood in both places, you may have felt, without quite knowing why, that they were somehow the same place. That the air had the same hush to it, that the bones of the land beneath you were speaking in the same language. And here is the thing I want to give you tonight, the small and astonishing thing that we will spend the next while turning over together in the dark. They are the same place. The mountains of Scotland and the mountains of North Carolina are not merely alike. They are not cousins, not echoes, not two separate ranges that happen to resemble one another. They are one single mountain range, one unbroken chain of rock raised in a single vast event hundreds of millions of years ago, and then torn cleanly in two, torn apart by the slow opening of an entire ocean that pushed its way up between them and carried the halves away from each other across the curve of the world. The Atlantic Ocean was not always there. There was a time, and it was a very long time, when you could have walked from the Scottish Highlands to the forests of the Appalachians without ever touching the sea. The same range, continuous, unbroken, a single great spine of mountains running on and on through what is now Scotland and Ireland and Wales, and the long border of Norway and Sweden, and the eastern coast of Greenland, and down through eastern North America. All of it one, all of it joined, and then, beginning around 200 million years ago, the ground itself began to pull apart along an ancient seam. A crack opened where the continents had been welded together, and the ocean came flooding into the gap. Slowly, so slowly, a few centimeters a year, no faster than your fingernails grow, but a few centimeters a year, given 200 million years, becomes 3,000 miles of open water, and the single range was split down the middle, and one half drifted east with Europe, and the other half stayed behind with North America, and the ocean filled the wound between them and kept on widening, and it is widening still tonight, while you lie there, a fraction of a hair's breadth wider than it was this morning. That is the first quiet wonder of this story. Scotland and Appalachia are torn halves of one mountain. But it is not even the strangest thing about them, because there is something else these two ranges share, something hidden, something nearly forgotten. And it is this: nobody remembers how tall they once were. Nobody who was there to see it survived to tell us. And nobody, looking at these gentle, worn hills today, would ever guess. Because these soft green mountains, these rounded, patient hills that feel so humble and so old, these were once giants. Let me say that again slowly so it can settle. The Appalachians that you see today, the highlands that you see today, the worn and gentle stumps of stone, they are not small mountains. They are the eroded remnants of mountains that once stood as tall as the Alps. Perhaps in their highest places, nearly as tall as the Himalaya. We cannot know the exact number. No one measured them, there was no one to measure them. The highest peaks may have reached 4,000 meters or 5,000 or 6,000 meters and more. And the honest truth is that this is an estimate, a careful reconstruction, not a figure carved in certainty. But the scale is real. These tired hills were once a roof of the ancient world. They were a wall of stone reaching up into thin, cold air, crowned with snow, sheer and sharp and young, the kind of mountains that take your breath simply to look at. And they have been dying ever since, quietly, gently, for something close to 300 million years. That is the master mystery we are going to wander into tonight, you and I, slowly, with no need to reach the end. How does a mountain that touched the sky become a soft green hill you could stroll up on a summer afternoon? What tears down a giant? And how long, how impossibly long, does it take? Because the agents that do this work are not violent. They are the most patient forces in all the world. And yet, given enough time, and the Earth has nothing if not time, they reduce the tallest mountains on the planet to gentle rolling ground, and then, eventually, to nothing at all. We will get to all of it. The rain that dissolves stone, the ice that pries it apart, the strange and beautiful fact that mountains have roots reaching deep into the molten rock below, and that as their peaks are stripped away, they float slowly upward, fighting their own disappearance for 100 million years and more. We will visit the Himalaya, still rising tonight, still pushing higher into the sky a little each year, and we will see in them a clock, a window onto what the Appalachians once were, and a glimpse of what the Himalaya themselves will one day become. We will follow the great slow rhythm of oceans opening and closing, the breathing of the planet across hundreds of millions of years, and we will arrive gently at the quietest truth of all, that nothing is permanent, not even the mountains, and that there is a strange peace in that if you let it in. But all of that is for later. We have all night. There is no rush. Before we go further, I want to do one small, warm thing. I would love to know where in the world you are listening from tonight, whether you are somewhere cold with the wind at the window, or somewhere warm with the air still and heavy, whether it is late evening or the deep middle of the night where you are. If you feel moved to leave a word in the comments and tell me where you are, I would genuinely like to know. There is something lovely about imagining all these quiet rooms scattered across the world, all these people drifting towards sleep at the sound of the same slow story. And if you are new here and you would like more of these long, unhurried journeys into the deep past, you might consider subscribing so the next one finds its way to you when you need it. That is all. No hurry, let your eyes close whenever they want to. The story will keep going and it will hold you the whole way down. Now, Let us go back to the mountains and let us ask the first real question, the one that anyone would ask. How could we possibly know how tall these mountains were 300 million years ago, when there was no one alive to see them, no instrument to measure them, nothing left of those towering peaks but worn-down hills? It sounds like the kind of thing no one could ever know. And yet we do know with real confidence, and the way we know it is one of the most quietly beautiful ideas in all of geology. So let me lay it out for you, slowly, piece by piece, the way you might lay smooth stones in a row. Here is the first stone. When you stand on certain high ridges in the Appalachians today, when you stand on the bare grey rock at the crest of some long, worn mountain, you are standing on a kind of stone that could only have formed deep, deep underground. Not a few meters down, not a few hundred kilometers down. In some places, the rocks now exposed at the very top of the ridges are rocks that crystallize 10, 15, even 20 kilometers beneath the surface of the Earth. They are metamorphic rocks, rocks that were cooked and squeezed and remade under enormous pressure and enormous heat. The kind of pressure and heat you only find when you have an immense weight of other rock pressing down on you from above. Let that settle for a moment, because it is a strange and powerful thing. The rock beneath your feet on the very summit of the mountain was once buried 20 kilometers underground. So where did all the rock that used to be above it go? Where is the 20 kilometers of stone that once lay on top of these rocks, pressing down on them, making them what they are? It is gone. All of it. Every bit of it. Worn away, carried off, grain by grain, by rain and river and ice, down off the mountains and out to the sea, over hundreds of millions of years. The mountain that you see today is not the mountain that was. The mountain that was had 20 kilometers of additional rock stacked above these summit stones, an unimaginable mass of stone reaching up and up into the sky. And all of that entire towering overburden, has simply ceased to exist as a mountain. It has been dissolved, broken, washed away, and laid down somewhere else as sand and silt and sediment, the dust of a giant scattered across the floors of vanished oceans and the deltas of long-dead rivers. This is how we know they were once enormous. The rocks themselves remember the weight that used to press upon them. The deep stones now exposed at the surface are like a watermark left on a wall after a flood. They tell you exactly how high the water once rose, even though the water is long gone. To bring rock that formed 20 kilometers down all the way up to the open air, you must remove 20 kilometers of material from above it. And the only way to do that on a mountain is to wear the mountain down from a colossal height to the gentle thing it is now. The stones do not lie. They were down there in the dark and the heat once, and now they are in the wind on the ridgetop. And the only honest explanation is that a mountain of staggering size once stood above them and is now entirely gone. Here is the second stone in the row. Today, the highest peak in the entire Appalachian chain is a mountain called Mount Mitchell in North Carolina, and it stands 2,037 meters above the sea, a little under 6,700 feet. That makes it the highest point in all of eastern North America, the very crown of the range, the tallest thing for 1,000 miles in any direction. And yet, set it beside what these mountains once were, and it is humbling almost to the point of tenderness. 2,000 meters where there once stood 4 or 5 or 6,000 meters and more. Mount Mitchell is not a tall mountain pretending to be old. Mount Mitchell is what is left. It is the worn remnant, the surviving stump, the highest piece of a giant that the patient forces of the world have not yet finished taking down. Stand on its summit, in the cool air, with the blue ridges falling away on every side, and you are standing on the last high ground of a range that once reached more than twice as far into the sky, and is still, slowly, year by year, sinking back toward the level of the land. And here is the third stone, the deepest one, the one that reaches furthest back into time. Beneath all of this, beneath the Appalachians, beneath the rocks that crystallize 20 kilometers down, beneath even the mountain building that raised the Great Range, there lies an older foundation still. Geologists call it the Grenville Basement, and it is the ancient bedrock upon which so much of eastern North America is built. And that basement rock is old in a way that is difficult for the mind to hold. It is over 1 billion years old, somewhere between 1 billion and 1,100 million years old, 1,000 million years and more. I want to give you a moment with that number because numbers like that wash over us if we let them, and this one deserves to be felt rather than merely heard. 1 billion years. The mountains we have been talking about, the great Appalachian Range, at its towering height, are some 300 million years old, and that already stretches the imagination to its limit. But the foundation beneath them, the Grenville Basement, is more than 3 times older than that again. It was already ancient, already a vast age of the earth lay behind it, before the mountains we have been describing were ever raised. Whole oceans had opened and closed above it. Whole mountain ranges older even than the Appalachians had risen and been ground entirely to dust upon it before the story we are telling tonight had even begun. So when you stand on those worn green hills, you are standing on a layered manuscript of deep time. At the very surface, the latest chapter, the soft, eroded crown of mountains, 300 million years dying. Beneath that, rocks that remember being buried 20 kilometers down beneath peaks that no longer exist. And beneath even those, a foundation older than 1 billion years, older than the mountains, older than the imagination, can comfortably travel. The whole thing is a record. The whole thing is a memory written in stone. And it is telling us plainly, if we know how to read it, that the gentle hills of Scotland and the gentle hills of North Carolina were once a single mountain wall as high as the greatest ranges of the modern world. It is worth pausing here in the warm dark to feel how strange that is. Because we carry, all of us, somewhere deep inside, the idea that mountains are the very symbol of permanence. In nearly every culture that has ever lived among them, mountains have stood for the things that do not change. We say a thing is as old as the hills. We speak of moving mountains as the very image of the impossible. We place the homes of gods upon their summits because the summits seem eternal, untouchable, beyond the reach of time and weather, and the slow ruin that takes everything else. The mountain is the thing that abides. The mountain is the thing that was here before us and will be here long after us, unchanged, immovable, fixed. And it is one of the gentle ironies of this story, one of the things that gives it, I think, its quiet poetry, that this is simply not true. The mountains are not permanent. They are not even close to permanent. They are among the most temporary great features the earth produces. They rise and they are worn down and they vanish, and the ground they once towered over fills with their remains, and after them new mountains rise from new collisions, and those too are worn down and vanish in their turn. The mountains are not the still point around which everything else changes. The mountains are themselves changing all the time, faster than we can see, but never for one moment standing still. They are passing through exactly as we are passing through. They are only slower at it. The hills of Scotland are dying. The hills of North Carolina are dying. They have been dying for 300 million years, gently, quietly, without complaint, and they will go on dying for a long while yet, sinking back toward the sea grain by grain, until one far-off day they are nothing but flat ground, a plain where mountains used to be, the way there are already such plains scattered across the world where even older mountains once stood and now stand no longer. But here is the part that I find most beautiful, and it is the part we will spend much of the rest of the night uncovering. The mountains do not go quietly because they are weak. They do not erode away in a few short million years, the way you might expect such soft and patient forces to manage. They take hundreds of millions of years to die, far longer than the raw arithmetic of erosion would ever suggest, because the mountains fight back. They resist their own disappearance. They have roots, deep roots, reaching far down into the hot and yielding rock below the crust. And those roots do something extraordinary, something that turns the simple story of demolition into something stranger and more tender. As the rain and the ice and the rivers strip the mountains from above, the mountains rise from below, floating slowly upward to replace what is lost, lifting their deep buried stones toward the light, refusing for 100 million years and more to simply lie down and be gone. We will come to all of that. We will come to the rain that drinks the stone, and the ice that splits it, and the rivers that carry the giant out to sea. We will come to those deep roots and the slow, buoyant rising. We will come to the living Himalaya, climbing higher into the sky even now. There is no need to reach any of it tonight. There is only the slow walking and the dark room, and the breath going gently in and out. For now, simply hold the one quiet thing we have found, that the soft green hills on both sides of a great grey ocean are halves of one torn giant, that they once stood as tall as the Alps, perhaps near the Himalaya, and have been worn down to gentleness over a span of time so vast it dissolves the mind, that the very rocks beneath our feet are the deep, cooked stones of a vanished height, lifted into the air by forces we have not yet uncovered, and that nothing, not even the mountains, the oldest symbol of permanence the human heart has ever reached for, nothing stays. Let the wind move at the window wherever you are. Let the room go soft. We have only just begun, and there is no end we need to reach. The mountains have waited 300 million years to be worn down. They will not mind if you fall asleep before we finish telling how. So begin where the wonder begins, with the two coasts and the single mountain between them. Stand for a moment on a ridge in the Scottish Highlands in the cool, wet air, with the heather running off in every direction and the grey light lying flat across the hills. The rock under your boots is hard and old and quiet. Now cross an ocean. Cross the whole grey width of the Atlantic, 4,000 kilometres of water, and come ashore in North Carolina and walk up into the Appalachian forests, into the green shade and the slow mist that hangs in the hollows. The rock under your feet there is the same rock, not similar, not a cousin, the same. The Scottish Highlands and the southern Appalachians are two pieces of one mountain range, a single chain that was once continuous, one unbroken spine of high country, before an ocean opened straight through the middle of it and carried the halves away from each other into two different worlds. We call the European half the Caledonides after Caledonia, the old name for Scotland, and the chain does not stop at the edge of Scotland. It runs up through the Scottish Highlands and across to Ireland and down into Wales. It reaches across the sea, into Scandinavia, into the long border mountains of Norway and Sweden, the Scandies. It even appears in the rocks of eastern Greenland on the far cold coast. And then on the other side of the Atlantic, it carries on, as the Appalachians, down the eastern side of North America. One range. Shattered across continents that did not yet exist in their present shape, scattered by an ocean that had not yet been born. Nobody remembers how tall they were. There is no one to remember. There were no eyes to see them at their full height, no hand to measure them, no word written down. The peaks that reached up into the ancient sky have been gone so long that everything which could have witnessed them has itself turned to stone and dust and been carried out to sea. We were not here. Our whole species, every human life that has ever been lived, would fit many times over into the time these mountains have spent dying. So we do not remember. We can only read what is left, the way you might read a single torn page and try to imagine the book. And the page that is left tells us something the mind can barely hold. These gentle green hills, these soft, worn shoulders of the Appalachians that look as though they have always been low and rounded and kind, once stood as tall as the Alps, perhaps taller. The careful estimate, and we should hold it carefully as an estimate and not a measured truth, is that the highest peaks may have approached the scale of the Himalaya, 4,000 meters, 5,000. Perhaps at the very greatest, more than 6,000 meters reaching up into the air. Picture that. Picture the soft blue ridges of the Blue Ridge Mountains, the ones that fade fold on fold into the haze, replaced by jagged white peaks far higher than anything in eastern North America today, peaks with snow on them through the long seasons, sharp and young and enormous. That is what stood here once, and it has been dying quietly without violence for something close to 300 million years. 300 million years? Say it slowly, in the dark, and let it stretch out and lose its edges. It is not a number the body can feel. So set it against something. The dinosaurs, the whole long age of them, came after these mountains had already begun their slow decline, and the dinosaurs are themselves an unimaginable distance behind us. The mountains were old before the dinosaurs were new. They were already wearing down grain by grain, while the great reptiles came and ruled and vanished, and they kept wearing down through all the ages that followed, patient and unhurried, all the way to this exact night, to the hills you might have driven past, to the rounded blue ridges that look so settled and so permanent and so calm. Wherever you are listening from tonight, let me know. It is a strange and lovely thing to think of all the different places a single quiet voice can reach in the dark, all the different windows with the night pressing against them, all the different beds. Tell me down in the comments where in the world you are lying as you listen to this. I read them. And if you are new here and you would like more slow walks like this one into old and buried things, you might gently subscribe and then drift off and let it be there for the next night you cannot sleep, because that is all we are going to do. We are going to walk down into this one mystery, slowly, the way you would walk down into a cave by lamplight, letting your eyes adjust, taking each step without hurry. We are going to find out how a mountain dies and how it fights its dying, and how we can possibly know any of it when no one was here to watch. There is no need to stay awake for the answers. The mountains have kept them for 300 million years. They will keep a little longer. So begin with the first question, the one that catches in the mind the moment the claim is made. If these soft hills were truly once Himalayan, how could anyone possibly know? You cannot measure a mountain that no longer exists. You cannot stand a ruler against a peak that crumbled to nothing before the first fish crawled onto land. And yet the height is not a guess pulled from the air. It is read from the rocks themselves, and the rocks are honest if you know how to listen to them. Here is the first strange piece of it. The rock that lies exposed today along the tops of the Appalachian ridges, the rock you would put your hand on if you climbed up there, did not form at the surface. It formed deep underground. In many places, the metamorphic rocks now sitting at the very top of the range crystallized 10, 15, even 20 kilometers below the surface of the earth, down in the heat and the crushing pressure where stone is cooked and folded and remade. Stop on that for a moment. The stone on the high ridge was once 20 kilometers down. which means that everything that was once above it, an entire mountain's worth of rock, 20 kilometres of overburden, the whole towering height that pressed down and cooked those deep stones into being, all of it is simply gone, worn away, carried off grain by grain, and washed out to the sea. To bring those deep-cooked rocks up into the daylight, the mountains had to lose from the top a thickness of rock greater than the height of any mountain standing on Earth today, and so the height becomes real, not as a measured number, but as a necessary one. The deep rocks are at the surface. The deep rocks could only get there if the great height above them was stripped away. The mountains had to have been enormous because only an enormous mountain has that much stone to lose. The highest thing left of all that lost grandeur in the eastern half of the torn range is Mount Mitchell in North Carolina. Mount Mitchell rises to 2,037 meters, 6,684 feet, and it is the highest point in all of eastern North America. Stand on its summit, and there is nothing higher between you and the Atlantic, nothing higher in any direction across half a continent. And yet it is a remnant, a stump, a worn nub of stone left standing after the giant came down around it, holding the modest crown of a fallen king. 2,000 meters where once perhaps 6,000 reached into the sky. That is the measure of what has been lost, standing there in plain sight, looking for all the world like it has always been exactly this size. And the rock, even of Mount Mitchell, even of these worn ridges, is older still than the mountains that rose from it. Down at the root of the Appalachian belt lies a foundation geologists call the Grenville Basement, stone that formed more than 1 billion years ago, around 1,000 to 1,100 million years before the present. 1 billion years. The mountains we are speaking of, the Himalayan giants of 300 million years past, were themselves built upon a floor of rock more than 3 times older than they were. Layer beneath layer of vanished time, each one the grave of something that came before, and all of it lying quiet now beneath the green and the mist and the slow blue ridges waiting in the dark. So that is what has been lost. The question that remains drifting in the dark is, what did the losing? And the answer is not dramatic. There is no single catastrophe to name, no day when the mountains fell. What dismantled the great Appalachian Caledonian colossus was something far quieter, far more patient, far more relentless than any eruption or earthquake. What took the mountains down was rain, and cold, and time. Begin with the rain, because the rain is everywhere, and it never stops. When water falls through the atmosphere, it dissolves a small portion of the carbon dioxide that drifts there in the air. Not much, just a little. Enough to make the water very slightly acidic. Carbonic acid, weak and gentle, the same mild acid in a glass of sparkling water. You would not notice it on your tongue, but rock notices. Specifically silicate rock, the granite and the gneiss and the feldspathic stone that makes up the bulk of mountain ranges, is dissolved by this slightly acid rain over time. Not quickly. Not in any way you could watch. The rain falls on a ridge and runs across the stone and carries away a quantity of mineral that you would need a laboratory instrument to detect in any single rainfall. The stone looks exactly as it did before. The mountain looks exactly as it did before. Nothing appears to have changed, but the rain comes tomorrow, and the day after, and across 1 million years, and across 10 million years, and across 100 million years, the cumulative dissolution is not nothing. It is kilometres. This process, chemical weathering, works in the joints and cracks of rock as much as on the open surface. Water seeps into the fine cracks in granite, the hairline fractures in gneiss, the spaces between mineral grains, and it sits there, in contact with the rock, not merely running across it, but in sustained chemical conversation with it, dissolving the feldspar and the mica grain by grain, turning solid crystalline stone gradually into a kind of mineral porridge, loosened material that rivers and gravity can then carry away. The rock does not shatter, it does not explode, it softens. And in softening, it yields. The warmer and wetter the climate, the faster this chemistry runs. A hot, rainy tropical highland weathers its rock faster than a cold, dry Arctic peak, because heat is energy, and energy accelerates reaction, and rainfall brings both the acid and the transport. Over geological time, this means that the same range will shed its stone at different speeds depending on where it happens to be on the planet, and at what epoch, and what the climate is doing around it. The ancient Appalachians, slowly drifting with the North American plate, have spent time in warmer climates and cooler ones, wetter eras and drier ones, and through all of it, the chemistry continued, slow and patient, dissolving the high places grain by grain into the rivers and the sea. But rain is only the beginning. There is a second agent, and it operates differently. Not by dissolving, but by splitting. Water has a peculiar property. When it freezes, it expands, not by a little, by roughly 9% of its volume. 9% sounds like an abstraction, but think of it this way. Water finding its way into a crack in a granite boulder, a crack perhaps the width of a coin filling that crack, and then, on a cold night, freezing. The ice that forms is 9% larger in volume than the water that entered. The crack is not 9% larger, the crack is the same size as before, and so the ice pushes. It pushes outward against the walls of the crack with enormous force, forces measured in tens of megapascals, enough to exceed the tensile strength of many common rock types. The rock cannot give the ice room, and so the rock eventually gives way. This is frost wedging, sometimes called freeze-thaw weathering, and in the high places where temperatures cross back and forth across the freezing point, which happens many times a year in an active mountain range, especially in the shoulder seasons of autumn and spring. It is ferociously effective. A single crack, opened fractionally by one winter's cycle of freezing and thawing, is now a slightly wider crack. Water enters more easily next time, freezes more fully, pushes harder. The crack widens further. Eventually, the block of rock above the crack is free to move, and it does, it falls. High mountain ridges in a tectonically active range are scattered with frost-shattered rubble, great angular blocks and slabs and chips of stone that have been levered off the parent rock and piled at the foot of cliffs. Geologists call these accumulations talus or scree. In the ancient Appalachians today, talus fields are far smaller and less active than they were during the ice ages, when the climate was colder and the freeze-thaw cycle more violent. But you can still find them, piles of angular grey stone resting on the lower slopes, the slow residue of uncounted cold nights, each one a small chapter in the long story of a mountain taking itself apart. The rivers carry what the weathering loosens. A river, even a gentle one, even a river that looks placid and quiet in summer, is a conveyor. It carries dissolved minerals in solution, the invisible product of chemical weathering, the calcium and the silicon and the magnesium that were once the inside of a mountain, now moving quietly in the water in a form you cannot see. It also carries suspended particles, clay and silt, visible as the slight muddiness of any river in flood, each tiny particle a fragment of stone that the frost and the rain and the roots of plants have set free. And it carries bedload, larger particles, sand and gravel, and in flood conditions boulders rolled and bounced along the riverbed, grinding against the channel as they go, wearing both the rock and themselves in the slow process of abrasion. The rivers that drain the Appalachians today are these: James, the Potomac, the Susquehanna. The rivers flowing east to the Atlantic and west to the interior carry sediment constantly. They have been doing so for hundreds of millions of years. The sediment fans out on the continental shelf, piles up in the quiet deep water, and accumulates. Geologists measuring the volume of sediment on the Atlantic coastal plain and continental shelf, the material that has been stripped from the Appalachians and deposited in the sea, find quantities that correspond to the loss of kilometres of rock from the ancient mountain belt. The rivers are not simply decorating the landscape, they are the drain. They are the mechanism by which the mountains leave. Glaciers did the same work, and when they were active, they did it with far greater violence. The ice ages, and there were many of them, cycling through the Pleistocene over the last 2.5 million years, and earlier ice ages reaching far deeper in geological time, drove glaciers south across the northern Appalachians and deeply into the Caledonian Mountains of Scotland and Scandinavia. A glacier is ice under pressure, and under pressure ice flows, deforming slowly like an enormously thick and cold and heavy syrup, and as it flows it carries with it all the rock it has scraped from the valley floors and carved from the walls. Glaciers gouge. They pluck rock from the bedrock beneath them, incorporating it into the ice, and then they carry it, sometimes hundreds of kilometres, before depositing it when they melt. The valleys of Scotland, the Scottish lochs with their extraordinary depth and length, were carved by glaciers. The lakes of Norway and Sweden, some of them plunging to remarkable depths, were carved by glaciers grinding along the ancient Caledonian route. The rounded, polished summits of the Appalachian peaks, so different from the jagged arêtes of a young alpine range, bear the marks of old ice, stone that has been overridden and smoothed by glaciers that have since retreated and vanished. And then there is the simplest force of all, gravity. You do not need water to move rock down a mountain. You need only the mountain to be steep and the rock to be free, and gravity will do the rest. Mass wasting is the collective term for all the ways that loosened material moves downhill without being carried by water or ice. Rockfalls, where individual blocks or slabs detach and tumble. Landslides, where a large body of rock and soil gives way along a failure plane and moves rapidly downslope. Soil creep, where fine particles move almost imperceptibly, a millimetre or two a year, drawn by gravity down the gradients of hillsides. None of these are dramatic on a human timescale except the landslides, which announce themselves loudly and briefly. But across geological time, they are continuous. Every loosened rock eventually falls. Everything made free by frost wedging and chemical weathering and root action eventually moves downhill, eventually reaches a river, eventually reaches the sea. The combination of these forces, chemical weathering dissolving stone, frost wedging splitting it, rivers carrying it, glaciers grinding it, gravity moving everything downhill, is what dismantles a mountain. Not one of them is spectacular. Not one of them would hold your attention for more than a moment in any given hour, on any given day. And yet, the record of what they achieve, written in the rock itself, is almost incomprehensible in its scale. Consider a number. The Appalachian Mountains, in their quiet present state, erode at roughly 10 to 30 meters per million years. Geologists express this sometimes as a few hundredths of a millimeter per year. To put that in terms that connect to something human, your fingernails grow at somewhere around 30 to 50 millimeters per year. The Appalachians in the same year lose perhaps 2/100ths of a millimeter to erosion. The mountain moves more slowly than your nail. The mountain moves at a pace that makes your nail seem by comparison a racing thing. And yet, given enough time, Not years, not thousands of years, but millions of years and tens of millions and hundreds of millions. Even this pace is sufficient to remove kilometres of rock. 10 meters per million years maintained for 300 million years is 3,000 meters, 3 kilometers of stone gone. And if the rate was somewhat higher in the distant past, when the range was taller and steeper and the slopes more aggressive in their shedding, as the models suggest, then 5 kilometers or more begins to seem not only plausible but necessary to account for what we can observe. How do we know these numbers? How does anyone measure the erosion rate of an ancient mountain range? This is one of the genuinely beautiful stories in the science of the Earth, and it is worth following slowly because the method is as quietly astonishing as the result. Imagine a rock at the surface of the ground, a boulder say, or a flat outcrop of granite on an Appalachian ridge. That rock is being struck continuously by cosmic rays. Cosmic rays are high-energy particles arriving from space, from supernova explosions and other violent events in the galaxy, and they rain down on the Earth's surface at a known and measurable rate. When these cosmic rays strike certain minerals in rock, they produce new atoms, atoms that would not be there otherwise, atoms of elements that the rock does not naturally contain. One of the most useful of these is beryllium-10, written as 10Be, a specific isotope of the element beryllium produced in the mineral quartz when cosmic rays strike the silicon and oxygen atoms that quartz is made of. The longer a rock has been sitting at the surface, exposed to those cosmic rays, the more beryllium-10 it accumulates, and beryllium-10 accumulates only in the top few meters of rock. Cosmic rays cannot penetrate much deeper than that. A rock sitting 20 meters below the surface accumulates almost none. A rock at the surface accumulates it at a measurable, steady rate. This gives geologists a clock. Take a rock from a ridge, measure the amount of beryllium-10 in its quartz, calculate how long that rock must have been sitting at the surface to have accumulated that much. If the rock has not been there long, if it was buried until recently and erosion has only just exposed it, the count will be low. If it has been sitting there undisturbed for millions of years, the count will be high. From this you can derive how fast erosion is proceeding, how quickly the land surface is being stripped away and replaced by rock from below. Paul Bierman, a geologist at the University of Vermont, and Milan Pavic, who worked with the United States Geological Survey, were among those who applied this technique to the Appalachians, drawing on river sediment as well as rock surfaces to get a broad average of erosion across the range. The beryllium-10 in Appalachian river sand, sand derived from the weathering of many rock types across broad drainage basins, tells you the average rate at which the whole watershed is being eroded, because the sand is a kind of blended sample of the whole. Their findings confirmed what the geology suggested. The modern Appalachians erode at something in the range of about 10 meters per million years, broadly consistent across the range, remarkably slow by any active mountain standard, a pace of almost archaeological delicacy. The range is being taken apart, slowly grain by grain, and the beryllium in river sand is how we count the grains. The measurement is quiet and technical, done in laboratories with mass spectrometers and careful sample preparation, far from the mountains themselves. And yet what it returns is one of the most vivid, imaginable windows into geological time. A scientist counts atoms made by stars exploding in the galaxy, atoms that found their way through space and atmosphere, and meters of solid rock to lodge in a quartz grain on an Appalachian ridgetop. And from the count of those atoms, she tells you how fast a mountain is dying. There is nothing in science more patient than that. But now the paradox opens. And it is a genuine paradox, the kind that, once you see it, makes the prior explanation feel incomplete. If the Appalachians erode at roughly 10 meters per million years, if that is the modern rate, confirmed by beryllium-10 in the river sand, then to remove 3 or 4 or 5 kilometers of rock, the math says you need 300 to 500 million years of steady erosion. And the Appalachians are in fact about 300 million years old in their current form from the Alleghanian orogeny, with precursor phases going back further. So the numbers can, with some generosity, be made to work. 300 million years of patient erosion at these rates could, in principle, have removed the overburden we infer was once there. But there is a problem buried in that accounting, a problem that, once you see it, changes the way you think about what a mountain is. Consider, if the mountain erodes, it loses mass. And if it loses mass from the top, if kilometers of rock are removed, then you might expect the surface to simply drop. The top comes off, the top of the rock becomes the new surface, lower than it was. Simple enough. Except that is not how it works, because a mountain is not sitting on a rigid floor. A mountain is floating. The crust of the earth, but the relatively thin, relatively cold, relatively rigid shell of rock that makes up the continents, is not resting on solid ground in the way that a stone rests on a table. It is resting on the mantle, the layer below, which is not liquid, but is not quite solid either. Over geological time, over thousands and millions of years, the mantle behaves like an extraordinarily viscous fluid. It flows slowly and profoundly under sustained pressure, and the crust, which is less dense than the mantle, floats in it. The way ice floats in water, or the way a raft of wood floats in the sea. A tall mountain range is heavy. Its weight presses the crust downward into the mantle, and the mantle flows aside to accommodate it, so the mountain range has a deep keel, a root, a downward bulge of crust extending into the mantle below. The taller the range, the deeper the root. The Himalaya and the Tibetan Plateau, the highest and most massive plateau on Earth, have a crustal root that extends tens of kilometers deeper into the mantle than the normal thickness of the surrounding crust. There is as much mountain below the surface as above it, in terms of the displacement involved. A vast, hidden iceberg of rock, invisible beneath the plains of Asia, balancing the peaks that pierce the sky above. This is isostacy. The word comes from Greek roots meaning roughly equal standing, equal weight, and it describes this buoyant equilibrium between the crust and the mantle. The principle was worked out in the 19th century when surveyors in India noticed that the Himalaya deflected their plumb lines less than expected, meaning the mountains had less gravitational pull than their visible mass suggested, implying a hidden deficit of mass below, a root of low-density crust reaching into the denser mantle. The calculation confirmed it. The mountain range was floating, and the part below the surface, the root, was less dense, less heavy than the mantle surrounding it, providing the buoyancy that kept the peaks in the air. Now, what happens when erosion removes mass from the top of a mountain range that is floating in this way? The answer is the mountain range rises. Not immediately, not overnight, but over thousands and millions of years as erosion strips weight from the surface of the range, the buoyant equilibrium is disturbed. There is less weight pressing the crust down. The mantle below, which has been displaced by the crustal root, now pushes back with more force relative to the weight above it. The crust rises, the root rises with it. The surface of the mountain, which erosion has been lowering, is pushed back up from below by the rebounding crust. This is isostatic rebound or isostatic uplift, and it is the reason that mountains do not simply erode down at the rate that the raw erosion numbers suggest. For every unit of rock stripped from the surface, the crust rebounds upward by a large fraction of that amount. The exact fraction depends on the relative densities of the crust and mantle, but it is substantial, somewhere in the range of perhaps 4/5, meaning remove 1 meter of rock from the top, and the surface only drops by perhaps 1/5 of a meter because the range floats back up by 4/5 of the thickness removed. This is why mountains resist their own death. They fight back, not with volcanoes or earthquakes, not with any violent assertion, but with the silent, patient, buoyant force of crust floating in mantle. You strip the peak. The mountain rises. You strip it again. The mountain rises again more slowly now, the root thinning, the buoyancy decreasing as the crustal keel is gradually consumed. But the resistance continues for an extraordinarily long time, prolonging the life of the range far beyond what a simple erosion calculation would predict. And here is the further consequence of that rebound, the one that gives geologists some of their most vivid evidence for what is happening underground. When the mountain range rises, the rocks that were buried deep below, rocks that crystallized and metamorphosed under enormous pressure and heat many kilometers beneath the surface during the mountain building event, are slowly brought upward. Erosion removes the top. The whole range floats up a little. More rock is exposed at the surface. Erosion removes that. The range floats up again. More rock comes to the surface. Over hundreds of millions of years of this cycle, this slow double movement of erosion, removing from above, and rebound, delivering from below, the rocks that were once 20 kilometers underground are eventually at the surface, stripped of everything that was ever above them, exposed in the quiet air on the ridges of what are now gentle hills. When you walk a trail along the crest of the Appalachians and the exposed rock is metamorphic, schist, or gneiss, or amphibolite, rock with a foliated texture from the enormous pressures it endured, you are looking at stone that was, when the Alleghanian orogeny was at its height, perhaps 15 or 20 kilometers beneath the surface. Everything above it is gone. The erosion and the rebound together performed an act of excavation so vast and so slow that the human mind has almost no framework for grasping it. Not a single dramatic moment, but an unbroken sequence of moments, each one removing a fingernail's thickness of stone, each one met by a slow, floating rise from below, 300 million of them stacked end to end, until the deep heart of a Himalayan-scale mountain range lay exposed on the surface of what looks, to every passing eye, like nothing more extraordinary than a gentle green hill. And it is in that gap between how slowly erosion moves and how much rock has disappeared that the deeper question quietly arrives. If the Appalachians erode at only 10 to 30 meters per million years, if the patient wearing away of rain and frost and river advances at a rate slower than a human fingernail grows, then how, across even 300 million years, does a mountain range lose kilometers of stone from its surface? The arithmetic does not immediately resolve. 300 million years multiplied by 30 meters per million years gives roughly 9,000 meters, 9 kilometers of rock. That is a credible depth of removal, and yet the exercise, performed so simply, conceals everything interesting about how it actually happens. Because erosion does not move at a constant rate. It is not a steady, metronomic wearing, the same in every century and every age. Rain falls harder in some climates than in others. Ice advances and retreats. Rivers run full and then diminish. There were periods in the long history of the Appalachians when the climate was warmer and wetter than it is today, when the chemical dissolution of silicate rock by acidic rainwater proceeded more quickly than the cosmogenic beryllium studies of the modern landscape suggest. There were periods of glaciation when ice crept down into the higher elevations and carved and plucked and shattered in ways that far exceeded the background rate. The number, 10 to 30 meters per million years, is a long-term average, the kind of average that can only be taken across deep time, and like all averages, it smooths over the texture of what actually occurred. Rainwater is one of the oldest and quietest agents of geological work on this planet. It falls through the atmosphere and absorbs carbon dioxide along the way, and in doing so it becomes something slightly more than water. It becomes a weak carbonic acid, and when that acid falls on rock, particularly on silicate minerals, the stuff of which granite and gneiss and schist are principally made, it begins a conversation with the rock's chemistry that the rock always, eventually, loses. The minerals in the rock, stable under the conditions deep underground where enormous pressure and heat prevailed when the rock first formed, are not always stable under the cool, moist, low-pressure conditions at the Earth's surface. They dissolve. Not quickly, not in any way a human observer standing in a rainstorm would notice. But across 100,000 years, across 1,000,000 years, the surfaces of exposed rock grains are slowly consumed by that slightly acidic water, the ions carried away, in solution, flowing downhill, eventually reaching rivers, eventually reaching the sea. The rock does not break, it simply ceases to exist in its original form, carried away, dissolved, and invisible in water that looks perfectly clear. Alongside the chemistry runs the mechanics. Water has a property that seems almost trivially obvious until you consider what it means for a mountain. It expands when it freezes, by roughly 9%. And a mountain range is full of cracks. The rock is not a seamless solid, it is fractured and jointed, full of planes of weakness, left by the stresses of its formation and its slow journey toward the surface. Water finds those cracks. It seeps in during a wet autumn, and then winter arrives and the temperature drops below freezing and the water in the crack expands. 9% sounds like a small number until you calculate the pressure that expansion exerts on the walls of the crack when there is nowhere for the ice to go. It is enormous, far beyond what the rock's tensile strength can resist. The crack widens, a fragment is levered away. In spring, the ice melts, more water enters a slightly wider crack, and the next winter the process repeats. This is frost wedging, or freeze-thaw weathering. And in the high elevations where winter temperatures swing repeatedly across the freezing point, it is a devastatingly effective disassembler of what seemed like solid, eternal stone. The fragments fall, they accumulate at the base of slopes, rivers carry them away, and the mountain, so slowly it would be invisible to any observer with a merely human lifespan, loses mass. Rivers do the carrying. They are the great transport system of erosion, moving the products of weathering, the dissolved ions, the clay particles, the sand grains, the occasional larger fragment, from the higher ground toward the sea. A river draining an active mountain range carries an immense quantity of sediment visible in the brown or grey color of the water during high flow. Over millions of years, rivers have carried the former substance of the Appalachians out to the continental shelf and the floor of the Atlantic, where it lies now as thick accumulations of sediment, the unrecognizable remains of a mountain range that once cast shadows across a landscape nothing like the one that exists today. And there were glaciers. Not always, and not everywhere, but during the Pleistocene, the great ice ages that began roughly 2.5 million years ago and cycled repeatedly until the last major retreat around 11,000 years ago, glaciers shaped the higher elevations of the northern Appalachians with a thoroughness that chemical weathering alone could not have matched. Ice is an extraordinary erosional agent. It plucks blocks of bedrock from the surfaces it slides over. It grinds those blocks against the rock below, wearing grooves and striations into the bedrock that survive to this day, the signatures of ice that has long since vanished. It carries enormous loads of debris and deposits them far from where they originated. And then it melts, and the streams emerging from the melting ice carry yet more material toward the sea. All of this, the chemistry of slightly acidic rain, the mechanical violence of freezing water, the patient transport of rivers, the occasional fury of glacial advance, constitutes what geology calls erosion. And it is worth holding these agents in mind, not as abstractions but as physical processes happening right now on every exposed surface. The rain falling on the ridge tonight is dissolving the rock beneath it imperceptibly slowly, as it has dissolved it every night for 300 million years. A process vast beyond ordinary imagining, reduced to something visible and present. The sound of rain on stone, which is, if you listen for what it is, the sound of a mountain dying. The question of how we actually know the rate at which this dying proceeds is itself a quiet wonder. You cannot watch a mountain erode, you cannot set up an instrument at the beginning of the Carboniferous period and return at the end of the Permian to check the reading. The timescales involved are so far beyond the reach of direct observation that measuring erosion rates at all required the invention of an entirely different kind of clock, one written not in the rock's chemistry, but in the rocks themselves, in the atoms produced when the surface of the Earth is struck by cosmic rays. Cosmic rays are high-energy particles arriving from outside the solar system. When they strike atoms in minerals near the Earth's surface, in quartz grains in a riverbed, for example, or in the surface of an exposed boulder, they cause nuclear reactions that produce rare isotopes not normally present in rock. One of these is beryllium-10. Beryllium-10 does not exist in appreciable quantities in rock that has spent millions of years buried deep underground, shielded from the cosmic ray flux by the kilometres of stone above it. But as rock approaches the surface, as erosion strips the overburden away, it begins to accumulate beryllium-10 in proportion to how long it has been exposed and at what rate it has been moving upward through the surface zone. By measuring the concentration of beryllium-10 in river sand, which represents the averaged surface material of the entire drainage basin upstream, a geologist can calculate how quickly the landscape is eroding. This is what Paul Bierman and Milan Pavic and their colleagues did with the Appalachians. The beryllium-10 concentrations in Appalachian river sediments told a story of remarkable patience, erosion rates on the order of 10 meters per million year, consistent and slow, a landscape wearing down at a pace that is almost impossible to intuit, but is, in geological terms, entirely comprehensible. The method is not simple. It requires understanding the flux of cosmic rays at the latitude and altitude of the measurement, accounting for how the rays are attenuated by depth in the rock, correcting for the decay of beryllium-10 over time. It has a half-life of about 1.4 million years. But the physics is sound, the measurements are reproducible, and the answer they return is one that few people, standing on a wooded Appalachian ridge and looking out at the soft, rolling, unassuming hills around them, would guess. This landscape is being removed, atom by atom, grain by grain, at a rate invisible to any human sense, but measurable now by counting the atoms left behind by the oldest light in the universe. And here is where the deepest paradox of the Appalachians comes into its sharpest form. 10 meters per million years, over 300 million years, that gives 3,000 meters of removal, 3 kilometers. And yet the rocks at the surface of the ridge, as noted, were once 15 or 20 kilometers underground. The gap between 3 kilometers and 20 kilometers is not a rounding error. It is not an uncertainty in the beryllium measurement. It is the place where the full story of how mountains die and resist dying must be told. And it requires returning to the idea of isostacy and to the realization that erosion is not a simple subtraction, but a conversation between the surface and the deep, slow interior of the Earth. Think about the word isostacy for a moment. It comes from the Greek isos, meaning equal, and stasis, meaning standing, equal, standing. The name itself contains the idea, everything seeking its level, everything pressing toward balance, everything adjusting and compensating and shifting until the weight above and the weight below arrive at some kind of truce. It is a word that describes how the solid Earth is, in a way that matters enormously, not solid at all. The mantle beneath the crust is rock. Let that be clear from the beginning. It is not liquid magma in the sense of a lava flow, but it is rock under such pressure and at such temperatures that over timescales of thousands and millions of years, it behaves as something closer to an extraordinarily thick, slow fluid, a substance that flows, that gives way under persistent load, that rises when a weight is removed and sinks when a weight is added. Think of a block of wood floating in water. Press it down and it sinks, release it, and it rises. The water is not interested in what shape the wood takes or what kind of tree it came from, only in the weight pressing down on it and the buoyancy pressing back. The Earth's mantle works over geological time by exactly the same logic. The crust floats on the mantle, not metaphorically, literally, low-density rock sitting on denser plastic rock beneath it, and the whole system working to maintain balance across every square kilometre of the surface. Where the crust is heavy, where a thick pile of sediment or ice or a mountain range presses down, the mantle below yields and the crust sinks. Where the crust is light, or where a weight has been removed, the mantle pushes back and the crust rises. This adjustment is never instantaneous. It happens over thousands of years, sometimes millions. But it happens, it is happening right now, in places where the adjustment from past weights is still working its way through the system, and it is the key to understanding why the Appalachians still exist at all. Because here is the thing that most accounts of mountain erosion quietly pass over. When a mountain erodes, the weight at the top is removed. And when weight is removed from the top, the crust beneath, no longer pushed down quite so hard, begins to rise. The mountain is being dismantled from above. The land is rising from below. These two processes run simultaneously, and together they create something strange and beautiful and deeply counterintuitive. A mountain that is being worn down is also at the same time lifting itself up. It is not simply dying, it is fighting. A mountain range, in this sense, is not a pile of rock sitting passively on a flat surface, waiting to be washed into the sea. It has a root. It pushes down into the mantle just as it pushes up into the sky. The higher the peaks, the deeper the keel of crust extending downward beneath them, just like an iceberg, where the visible portion above the water is only the small fraction, the bulk hidden below the surface. The Himalaya and the Tibetan Plateau, the tallest and most massive topography on Earth today, have a crustal root that extends tens of kilometres deeper than the surrounding crust. The crust beneath Tibet is roughly twice the average thickness, around 60 to 70 kilometres thick, where it might normally be 30. All of that mass, all of that high-altitude plateau, and those peaks reaching nearly 9 kilometres into the sky, is balanced by an enormous keel of lighter crust pressing down into the denser mantle below. Now imagine rain. Imagine rivers. Imagine frost wedging open cracks in the rock, grain by grain, season after season. The summit of the Himalaya loses a little mass. The peak is fractionally lower. The weight pressing down on the mantle is fractionally less, and the crust, ever so slowly, floats upward to restore the balance. Not the full amount. The rebound is not 1-for-1, but a substantial fraction. For every metre of rock stripped from the surface, the crust rises something like 6 or 7/10 of a metre in response. The net loss in elevation is real, but it is far smaller than the amount of material removed would suggest. This is the answer to the gap. Remember the arithmetic from before? The Appalachians show about 3,000 metres of erosion if you take the beryllium-10 rates and multiply across time. But the rocks at the surface crystallized 15 to 20 kilometers underground. Where is the rest of the missing rock? The answer is in the rebound. As erosion removed the upper layers, the range floated upward. Deep rocks that had been buried far below the surface were carried slowly toward the light, not because the surface eroded all the way down to them, but because the entire mountain was rising slowly from below as its burden was relieved. The deep metamorphic rocks now exposed on Appalachian ridges did not simply sit there, patient and waiting, while 20 kilometers of material was washed off above them. They were carried upward, bit by bit, as the mountain itself rose to compensate. Erosion and rebound working together in a long, slow partnership, a partnership that geologists sometimes call unroofing. And unroofing takes an enormous amount of time, far more than the raw erosion rate suggests, because you are not simply removing material from a fixed target. You are removing material from a target that is rising toward you. It is like trying to empty a bucket that has a slow leak at the bottom, refilling it from below. You are making progress, but the bucket does empty eventually. But the refilling slows you down enormously, and the time required is many times longer than if the bucket was simply sitting still. This is why the Appalachians still exist 300 million years after the collision that built them. This is why the Scottish Highlands still rise above the Atlantic plain. This is why, after all that time and all that weather, and all those rivers carrying sediment to the sea, there is still a mountain to look at. The range has been fighting its own death, rising slowly from within, keeping itself alive for hundreds of millions of years, beyond what simple erosion would predict. The fight is not over. Mount Mitchell at 2,037 meters is still there, still high enough to catch cloud, still making its own weather. Still, and in the geological blink of the last few million years, the same worn, stubborn thing it has been for a very long time. There is a way to see this rebound not just as an abstract force, but as something the Earth is visibly doing right now, in places you could travel to and stand on, in places where the adjustment is not happening over millions of years, but over the course of human history. And it begins with ice. 12,000 years ago, 11,700 years ago to be closer, the last great ice sheets of the most recent glacial maximum were melting. Scandinavia had been buried under ice up to 3 kilometers thick. The crust beneath it had been pressed down by that weight, perhaps hundreds of meters, over tens of thousands of years. The mantle had yielded, the land had sunk, and then, geologically speaking almost overnight, the ice melted. The weight was removed, and Scandinavia began to rise. It is still rising. Today, right now, the land across much of Norway, Sweden, and Finland is lifting at a rate of several millimeters per year, in some places approaching a centimeter per year. Old harbors that were at sea level in Viking times are now noticeably above it. Beaches from thousands of years ago sit on hillsides well above the present shoreline. The Scandinavian land surface is documenting its own history in the rock, in the terraces and ancient strand lines that mark where the sea once stood before the land rose above it. The same process is happening in Canada. Hudson Bay and the land around it, pressed down by the immense weight of the Laurentide ice sheet, which at its maximum was perhaps 3 or 4 kilometers thick over much of Canada, is also still rising. Measurements from GPS stations show the land around Hudson Bay lifting by roughly 1 centimeter per year in some places. This is glacial isostatic adjustment, the technical name for the rebound of crust after the removal of an ice load. And it gives you a way to feel, in human scale, what isostacy means. The ice sheets that pressed Scandinavia down were enormous and heavy. They were there for tens of thousands of years, and yet they melted only about 11,000 years ago, not even halfway back to the time of the first written languages of Mesopotamia, almost nothing on geological timescales. And the crust is still adjusting, still catching up, still rising. The mantle is slow, but it is patient, and it does not forget that it was pushed. Now scale this up. Not kilometres of ice for tens of thousands of years, but kilometres of rock for hundreds of millions of years. The Appalachians and Caledonides carried a load of crust that was far more massive, far more persistent, and the rebound from losing it was and continues to be proportionally complex and long-lived. The glacial isostatic adjustment we can measure in Scandinavia today is the fast, human-visible version of the same physics that has been operating in the Appalachians and the Scottish Highlands since the Alleghenian and Caledonian collisions, only spread across timescales so large that no single lifetime, no recorded history, no civilization has been long enough to watch it directly. And this brings up a question that geologists have been debating carefully and honestly for a long time, because the Caledonian Mountains, the Scottish Highlands, the Scandinavian Mountains, the Scandis, are old, very old. The Caledonian orogeny that built them ran from roughly 490 to 390 million years ago. The collision that assembled them is long finished. The tectonic force that built them has not been active for hundreds of millions of years. And yet when you look at the mountains of Norway, when you stand at the top of Guldhupiggen, at 2,469 meters, the highest point in Scandinavia, the view around you does not feel like the view from an ancient, exhausted ruin. It is dramatic, it is high, the fjords below are deep. The ridges are sharp enough. Why? Why are mountains that formed nearly 500 million years ago still meaningfully tall? Why has the simple arithmetic of erosion not reduced them to the low, rolling cratons they should, naively, have become by now? Ben Nevis in Scotland asks the same question. At 1,345 meters, it is the highest peak in the British Isles. It is the remnant of an ancient collapsed volcano, the eroded core of something that once rose far higher within the Caledonian chain. By any straightforward reckoning, it should be much smaller than it is. Scotland should be flatter. The maths of erosion rates applied to 400 million years should produce something closer to the Canadian Shield, old, flat, ancient basement rock at low elevation, than the distinctly rugged highlands that dominate northern Scotland and draw visitors from everywhere. This is an honest, open question in geology. It does not have a single settled answer. Several mechanisms have been proposed, and the truth is almost certainly a combination of them. One is the long-lasting isostatic effect of the deep, crustal roots themselves. Even without ongoing tectonic forcing, a thick root of low-density crust in the mantle will continue to provide some buoyancy, some upward push, for a very long time. The root does not simply disappear when the collision stops. It is still there, still lighter than the mantle around it, still pressing upward. Another proposed mechanism is something called dynamic topography. The idea that the flow of rock within the mantle itself, driven by differences in temperature and density deep within the Earth, can push up or pull down on the crust above it. The mantle is not static. It circulates slowly over millions of years, with hotter rock rising and cooler rock sinking in patterns that can deflect the surface up or down by hundreds of meters. A region of upwelling mantle beneath Scotland, for example, could be maintaining some of the Highlands elevation even in the absence of tectonic compression. And there is evidence, still being debated, that something like this may be operating beneath parts of the British Isles and Scandinavia, that the crust is being held up in part by the slow circulation of the mantle below. There is also the possibility of renewed tectonic or thermal influence. The North Atlantic, which opened beginning around 200 million years ago, was accompanied by enormous volcanic activity. The opening of an ocean involves rifting, which involves heat, which involves uplift. The British Isles and Scandinavia were in the vicinity of major thermal and tectonic events associated with the North Atlantic opening and the Icelandic hotspot, and these may have given some of the old Caledonian topography a kind of second life, a renewed pulse of uplift layered on top of what remained. None of these explanations is mutually exclusive. All of them may be contributing to varying degrees. The honest answer, which geology is comfortable giving because it is the true answer, is that we are still working this out. The persistence of relief in ancient mountain chains at passive continental margins is a genuinely active area of research, and Galdhøpiggen and Ben Nevis are, in that sense, open questions as well as beautiful destinations. What is clear is the Caledonian span itself. The sheer geographic reach of this one ancient system across what is now, because of the rifting of the Atlantic, widely separated landmasses. The Caledonides do not begin and end in Scotland, follow their geology northward through the Orkney and Shetland Islands and across to the eastern coast of Greenland, where Caledonian rocks appear in the same orientation and with the same ages as their Scottish counterparts. Follow them south and west through Ireland and Wales, where the ancient basement of these islands records the same collision, the same deep time event. Cross the Atlantic, following the logic of the break rather than the present geography. And the same chain reappears in the northern Appalachians of New England and the Canadian Maritimes. Then sweep northeast across the Norway-Sweden border through the great mountain spine of Scandinavia, the Scandis, whose rocks tell the same story as the Scottish Highlands in the same language. Caledonian age, Caledonian structure, Caledonian basement. Before the Atlantic existed, all of these fragments were a single continuous thing, a mountain range that stretched for thousands of kilometers across a continent that had not yet been torn in two. The Iapetus Ocean had closed completely, suturing these masses together. And the collision of Laurentia with Baltica and Avalonia had thrown up a chain of mountains that, at their greatest, may have been as impressive as anything the Earth has produced. The timing of the Caledonian orogeny puts its peaks at perhaps 400 million years ago, before the later Alleghanian event added the southern Appalachians, before Pangaea was fully assembled, at a time when the land surface of the Earth was already ancient but would have looked almost unrecognizable. And then, gradually, the rifting began. The process that would eventually open the Atlantic Ocean started at the edges. The crust stretched and thinned, the mantle began to intrude, volcanoes marked the initial tearing of the continent. By around 200 million years ago, the break had propagated far enough that seawater could reach the rift valleys. The Atlantic was born, and the great Caledonian Appalachian chain was torn in half, one piece staying with North America as it drifted westward, the other staying with Europe as it drifted east. An ocean grew between them, filling what had been dry land, separating mountains that had once been adjacent. The Irish Sea, the English Channel, and then the North Atlantic, widening, deepening, becoming the ocean we know today. Scotland and North Carolina did not drift apart because they were strangers. They drifted apart because they were the same place, broken. The rocks of the Scottish Highlands and the rocks of the New England Appalachians are identical in the way that matters most in geology, identical in age, identical in structure, identical in the chemical signatures of their formation. They are siblings. They are more than siblings. They are the same body, separated, and both fragments have been eroding ever since. The Scottish piece, now stranded on the European plate, subject to the North Atlantic's weather and the ice of multiple glaciations, has come down from whatever it once was to Ben Nevis's 1,345 meters and the rounded, heathered ridges of the Highlands. The North American piece, similarly glaciated in its northern extent, similarly subject to hundreds of millions of years of rain and river, has come down from whatever it once was to the forested, gentle ridges of the Appalachians, with Mount Mitchell at 2,037 meters as its highest surviving point. Both fragments are still in their way fighting. The isostasy beneath them has not fully resolved. The deep roots of the collision that built them have not fully disappeared. And in the Scottish case especially, the debate about dynamic topography and mantle flow adds genuine uncertainty about exactly how much of the present elevation is a legacy of the Caledonian orogeny, and how much is something more recent, more active, more complicated. This is what the landscape holds. Not just rock and heather in the particular angle of Atlantic light across a Scottish ridge. It holds the memory of a collision that happened 400 million years ago. It holds the slow, patient work of rebound that has been going on ever since. And it holds the open question of why it is still as high as it is, a question that researchers are still debating with the sophisticated tools of seismology and GPS and geodynamic modelling in the universities of Edinburgh and Oslo and Toronto and elsewhere. The Caledonian Range is, in this way, one of the most generous mysteries geology offers. It is not fully explained, and its present form is evidence of processes that are still operating right now beneath the ground that walkers cross when they climb toward the summit of Ben Nevis on a cloudy Scottish morning, or look out from Galdhøpiggen across the snow-covered Jotunheimen Plateau of Norway, or follow the coastal path in County Donegal in Ireland, where the ancient Caledonian basement breaks the surface in slabs of schist that are, if you know what they are, among the most remarkable things a hand can touch. There is something particular about putting your hand on a rock and knowing that it was once 20 kilometres underground. That knowing is not abstract in the way that knowing the distance to a star is abstract. It is intimate. The rock is right there, warm or cold depending on the weather, rough or smooth depending on how long the glaciers worked on it, and it has been on a journey that dwarfs anything human history contains. A journey from deep in the Earth's crust, where it crystallized under enormous heat and pressure, upward through the patient work of erosion and rebound and glaciation and everything else that geology does to a piece of rock over hundreds of millions of years, until it arrived here, at the surface, in the light, under a sky that knows nothing of where it came from. The Caledonian Range spread from Greenland to Ireland to Wales to Scotland to Norway. From Norway, if you follow the ancient Caledonian rock eastward and south, you eventually run off the edge of the orogeny and into the broader European craton, the old, stable interior of the European plate. The Skandes mark something like the eastern edge of the Caledonian story in Scandinavia, the line where the collision zone met the old basement of Baltica. Beyond it, the Baltic Shield, Fennoscandia, the ancient craton of Scandinavia, is itself one of the great worn-down remnants of even older mountain building, Precambrian terrains of vast age that have been at or near the surface for so long that the mountains they represent no longer exist even as stumps. They are the basement. The root of ranges that have not merely eroded but been entirely swallowed by geological time, billions of years of it, leaving only the deep crustal rocks that once lay 20 or 30 kilometres below, ranges we can no longer even name. This is the far future of every mountain range. The Caledonides are partway there, the Appalachians are partway there, the Baltic and Canadian shields are already there, already the flattened, worn, ancient basement of mountains whose peaks are as unreachable as a specific Tuesday morning 4 billion years ago. The land you would stand on if you walked across the exposed Canadian shield in northern Manitoba or Ontario is rock that was once buried deep within something that towered, but the tower is entirely gone, and what remains is only the foundation. And against all of this, against the 300 million year slow death of the Appalachians, the 400 million year wearing of the Caledonides, the billion-year reduction of the Precambrian shields to their present flatness, there exists today, on the other side of the planet, a mountain system that has not yet entered this story at all, except as a reference point. A system that is not dying, or not visibly so. A system that is, by every measurement available, still rising. still being built, still engaged in the great collision that creates mountains, rather than the long aftermath that destroys them, the Himalaya. India arrived at the Eurasian plate approximately 50 to 55 million years ago. It had been traveling for a long time before that, drifting northward from its position as part of the southern supercontinent Gondwana, crossing the Tethys Ocean, a great ancient sea that no longer exists in the way it once did, its floor mostly subducted away, its sediments plastered onto what would become the faces of the mountains that rose when the crossing was complete. India moved northward at speeds that were, by the standards of plate tectonics, remarkable, several centimeters per year, perhaps approaching as much as 15 or 20 centimeters per year during certain intervals of its northward journey. A racing plate, geologically speaking, burning across the ocean that separated it from the continent it was about to strike. The collision, when it came, was not like anything in the human experience of collision. It was not sudden. It did not produce an explosion that could be heard or a shockwave that could be felt. It was a coming together so slow that you would not, standing at the margin, perceive it as movement at all. But the forces involved were immense, and the crust had nowhere to go but up. The Tethys Ocean sediments, limestone and shale and sandstone, laid down on ancient seafloors, full of the shells and skeletons of marine creatures that had lived and died in warm, shallow water, were scraped off the descending plate and piled up at the collision margin. The continental crust of India, unable to subduct easily because it was too light and too thick, instead crushed into the Eurasian crust and forced it upward, and the Himalaya began. They are still rising now. India continues to push northward into Asia at roughly 4 to 5 centimeters per year, a motion so steady it has not paused in tens of millions of years, and the mountains it raises respond to that steady pressure by climbing. The commonly cited figure for Himalayan uplift is on the order of a centimeter per year, though the true picture is more nuanced than a single number suggests. Erosion removes much of what tectonics builds, and the net gain in surface elevation at any given point is smaller and varies considerably from place to place along the range. But the underlying drive is real, and it is ongoing. The Indian plate is not finished. The Himalaya are not finished. They are the living version of what the Appalachians once were, still in the middle of the story that the Appalachians have already, slowly, ended. And this is where the question of mountains dying becomes genuinely strange, because a mountain does not simply erode away the way a sandcastle dissolves in rising water. The situation is far more complicated than that and far more interesting, and the complication has a name: isostacy. Consider an iceberg floating in the sea. You see the portion above the waterline, white and bright, catching the light. But roughly 9/10 of the ice is beneath the surface, hidden in the cold, dark water below, holding the whole mass up. If you were to shave off the top of that iceberg, the visible peak would shrink, but the iceberg would not simply sink, it would rise. The reduced weight would allow the submerged portion to lift, and the surface you had just shaved would climb back toward where it was, not quite reaching it, but rising nevertheless. The ice floats in equilibrium with the water around it, and any change to the mass shifts that equilibrium, and the iceberg responds. Mountains rest on the mantle of the Earth in very nearly the same way. The continental crust on which they sit is less dense than the mantle rock beneath it, and so it floats buoyantly the way ice floats in water. And a mountain range with its great mass piled high above the surrounding land has a corresponding structure reaching downward, a root of thickened crust descending into the mantle far below the surface, providing the buoyant keel that supports the peaks above. The Himalaya and the Tibetan Plateau sit atop a crustal root that plunges tens of kilometers deeper than the normal thickness of crust elsewhere. The mountains you see in the sky above Nepal and Tibet are supported from below by a mass of rock that you cannot see at all, driving down into the plastic mantle the way the submerged bulk of the iceberg drives down into the sea. This has a profound consequence for erosion. As rain and rivers and glaciers and frost steadily remove material from the peaks and ridges of a mountain range, the mass of the range decreases. And as the mass decreases, the buoyant balance shifts. The crust, relieved of some of its load, rises. Isostatic rebound, geologists call it. The slow, steady upward spring of the land as the weight pressing it down is removed. The mountain, in effect, fights back against the forces wearing it down. For every unit of rock stripped from the surface, the range rises back up by a significant fraction of that amount because the deep root responds to the reduced load above by floating higher in the mantle below. The result is that to erode a mountain range to flatness takes far, far longer than a simple arithmetic of erosion rates would suggest. The surface is being lowered, yes, but the range is simultaneously rising, slowly, pushing itself back up, unroofing its own deep rocks as it does so. The metamorphic and igneous rocks you find today on the ridges of the Appalachians, rocks that crystallize tens of kilometers underground, under immense pressure and heat, are not there because erosion merely shaved off a thin surface layer above them. They are there because the entire thickness of rock that once buried them, kilometers and kilometers of material, was stripped away over hundreds of millions of years, while the range itself kept rising to compensate, keep pace, resist the loss. The deep rocks came slowly to the surface, not because the surface descended to meet them, but because the range rose, unroofing them into the open air over geological time spans that beggar the imagination. There is a way to see this process that requires no imagination at all, because it is happening right now, measurable with instruments, in a place you could visit. Scandinavia is rising, the land that holds Norway and Sweden and Finland. The old Caledonian roots beneath the modern cities and fjords is lifting at a rate of several millimeters to nearly a centimeter per year in some areas. Not because of any tectonic collision, not because any mountains are currently being built there, but because roughly 11,000 years ago, the great ice sheets of the last glacial maximum finally melted away. For tens of thousands of years before that, kilometers of ice had pressed down on the Scandinavian crust, loading it with an almost incomprehensible weight, depressing it into the mantle. When the ice went, that weight lifted, and the land began to rise back toward its former position. It is still rising now, thousands of years after the ice retreated. The process has a name: glacial isostatic adjustment, and it is the same fundamental physics as erosional isostasy, only faster and on a more human timescale, compressed enough that we can actually watch it. The same thing is happening in the Hudson Bay region of Canada, where the crust was also loaded with ice and is also still rebounding upward, years measured in thousands, not millions. These are not theoretical mechanisms. They are documented, ongoing, and measurable with modern geodetic instruments, the same satellite-based tools that track the movement of tectonic plates in real time. The principle that makes mountains resist their own death is not an abstraction. It is something you can observe directly, written in the slow rise of a coastline on the edge of the Arctic, carved in the changing waterlines of ancient harbors whose stone quays now sit further from the sea than they did when they were built. And yet the question is not fully resolved, because when you look at the Scandinavian mountains, the Scandis, rising along the border between Norway and Sweden, reaching their highest point at Galdhøpiggen, which stands at 2,469 meters, you're looking at mountains that have puzzled geologists in ways that go beyond simple isostasy. The Caledonian orogeny that built them ended somewhere around 390 million years ago. By most straightforward reckonings, mountains that old in a tectonic setting that has been relatively quiet since their formation should be far lower than they are. The Scandies are older than the Alps. They had, by rights, more time to erode, and yet they maintain a height that seems, by a naive calculation, surprising. Ben Nevis in Scotland, part of the same ancient Caledonian system, stands at 1,345 metres, the highest point in the British Isles, and in the broader scheme of things not very high at all, the worn remnant of what it once was. Ben Nevis itself is the eroded remains of an ancient collapsed volcano, a caldera that fell in on itself hundreds of millions of years ago and has been slowly flattened ever since. But even this is higher than a purely erosional model might predict. Across the Atlantic, the same logic applies to the Appalachians, where some researchers have asked why certain parts of the range maintain more topographic relief than the standard story of slow, steady erosion would straightforwardly produce. The honest answer, the one that most closely matches the state of scientific understanding, is that this is genuinely debated. Several processes have been proposed to account for the unexpected persistence of relief in old passive margin mountain ranges. One is long-lived isostatic support. The deep roots of these ranges have not yet fully equilibrated, and the crust is still, on timescales of millions of years, adjusting. Another is dynamic topography, the idea that flow within the mantle itself, deep currents of slowly convecting rock moving beneath the lithosphere, can push the surface upward from below, maintaining elevation that the surface geology alone would not sustain. And there is evidence in some regions for renewed episodes of uplift, tectonic or thermal pulses, long after the main orogeny that gave the range its original height. The Scandies in particular have been studied extensively in this context, and the conclusions remain unsettled. What is clear is that the Caledonian chain, wherever you find it, carries its age differently than the flat cratons that represent mountains even older and even more thoroughly worn down. Scotland, Ireland, Wales, the Scandies, the coast of East Greenland, these are the surviving fragments of one enormous range. And then there is the Himalaya. If the Appalachians and the Caledonides are the old dead, the mountains that have been dying for 300 million years, the ranges we study to understand what an ending looks like, then the Himalaya are the living. They are the counterpoint, the thing that is still becoming, still in the very middle of its own making, still rising out of a collision so enormous and so slow that it has been going on longer than our species has had language, longer than our genus has had fire. The story of how they came to be is a story about an ocean that no longer exists. Before the Indian subcontinent was where it is now, before the Himalaya were anything at all, there was a vast body of water that geologists call the Tethys Ocean. The Tethys was not a small sea. It stretched across much of what is now the landmass of Asia and Europe and North Africa, a warm, shallow, ancient sea, and on its floor, across millions of years, marine organisms lived and died and sank and accumulated, building up thick sequences of limestone and seafloor sediment, the compacted remains of creatures that never imagined they were laying down the raw material of the highest mountains the world would come to know. And then the plate-carrying India began to move. This was roughly 50 to 55 million years ago. The Indian plate, carrying the chunk of ancient crust that would become the subcontinent, had already been moving northward for tens of millions of years before the actual collision, drifting across what had been the southern hemisphere at a speed that geologists consider unusually fast for a major tectonic plate, something in the range of 4 to 5 centimeters every year. That does not sound like much. A centimeter is the width of a fingernail. 4 or 5 of them in a year is less than the length of a hand. But the Indian plate had been doing this not for a year, not for a decade, not for a human lifetime, but for tens of millions of years without pause. And over that span, at that pace, it crossed an entire ocean. The Tethys closed in front of it. This is not a metaphor. The oceanic crust of the Tethys was being consumed at subduction zones along the southern edge of Eurasia, pulled downward into the mantle as India advanced, and the sea that had filled that space for so long shrank and narrowed and eventually, as India drew close enough, disappeared. What had been a broad seaway became a suture. And then India arrived, and the collision began. Continent met continent. When two oceanic plates converge, one can slide beneath the other, carrying itself down into the mantle where it is consumed. But continental crust is too light, too thick, too buoyant for that. It resists being dragged down. So when India met Eurasia, there was nowhere for the pressure to go except up. The crust buckled and thickened. Rock that had spent millions of years on the floor of the Tethys, the marine limestone, the seafloor sediments, the compressed remains of ancient seas, was lifted. And it is still being lifted now. This is the fact that takes a moment to settle in. The Himalayas are not a completed thing. They are not a monument to some long-ago violence that has since quieted. India is still moving north. The rate is around 4 to 5 centimeters per year. The collision is ongoing, the pressure is ongoing, and the net result is that the Himalayas are still rising at a rate of roughly a centimeter per year. Some measurements suggest the uplift rate varies locally, 5 millimeters here, 10 millimeters there, but the broad picture is one of active, present tense growth. Every year that passes, the peaks are incrementally higher than they were the year before. Mount Everest stands at 8,149 meters. That figure comes from a joint survey conducted by China and Nepal in 2020, the most recent and precise measurement. Nearly 9 kilometers above sea level, the highest point on the surface of the planet. And near its summit, in the rock that has been lifted almost 9,000 meters into the air, there is limestone, marine limestone. Rock made of the compacted shells and bodies of creatures that lived on an ancient sea floor, creatures that belonged to the Tethys Ocean, that never knew air or wind or altitude. They have been carried by the slow grinding force of one plate pressing against another, from the bottom of a vanished sea to the top of the living world. Fossils of marine organisms have been found high on Everest. Ancient seafloor life in rock near the summit of the tallest mountain on Earth. There are few things in geology that make the scale and strangeness of this planet more immediate than that single fact. The top of the world was once the floor of an ocean. The same forces that wore the Appalachians down from their great Himalayan heights also, elsewhere, at other times, on other plates, lifted the bottom of the Tethys to the highest place the wind can reach. But the Himalayas are not exempt from what has taken the Appalachians down. Erosion works on them too, and it works ferociously. The rates are incomparable to anything we have measured on the quiet Appalachians. Where the Appalachians erode at something like 10 to 30 meters per million years, a slow, gentle, almost imperceptible wearing, the Himalaya erode locally at rates many times greater. Several millimeters per year in some places, expressed across a million years, that is thousands of meters, rates of removal that would strip a mountain bare in what is, geologically, a short span. The reason is everything that drives erosion operating at once and at extremes. The slopes are steep, and steep slopes mean fast-moving rivers that carry enormous loads of sediment. The Indian monsoon delivers immense quantities of rainfall to the southern face of the range, and that rainfall is the chemical weathering engine, the water acidic with dissolved carbon dioxide, dissolving silicate minerals at depth, undermining rock that then crumbles and slides. There are glaciers, there is frost wedging, there are earthquakes along the active faults that run through the collision zone, shaking loose what erosion has already weakened. The great rivers of the region, the Indus and the Ganges and the Brahmaputra, are doing what rivers have always done to mountains. They are carrying them away, grain by grain, stone by stone, out to the lowlands and eventually to the sea. The sediment that washes out of the Himalaya has built enormous fans on the floor of the Indian Ocean, deposits so thick and so extensive that they are among the largest sedimentary accumulations on the planet. The Himalaya are being ground to powder and delivered to the ocean even as they are being pushed upward. This is the battle. Uplift against erosion, locked in a competition that has been running for 50 million years and is nowhere near its conclusion. The Himalaya rise a centimetre a year. They lose immense quantities of rock to rain and river. The net result is a complex accounting varying by location, by season, by the particular geometry of each valley and each fault. In some places, the peaks genuinely gain net height. In others, erosion keeps pace with uplift or winds. The mountain range as a whole remains for now in something like a dynamic equilibrium, though equilibrium is almost too peaceful a word for what is happening. It is more like a standoff sustained by the continuous press of India against Asia, which shows no immediate sign of stopping. And this is where you can begin to see very faintly the far future. Because the standoff cannot last forever. It will not last forever. India is still moving, but the forces that drive plate motion are themselves governed by the heat of the planet's interior, by a planetary engine that has been running for 4.5 billion years and will not run at the same rate indefinitely. And at some point, in some configuration of tectonic events that is beyond our ability to predict with precision, but entirely within what the record of the past tells us is possible, the forces that hold the Himalaya up will begin, perhaps gradually, perhaps in fits and starts, to ease, and when that happens, the erosion, which never pauses, will begin to win. The Appalachians are the lesson. They show us what happens next. But to understand why this is not simply local geology, why it is not just the story of one range or one collision or one pair of continents, you have to go back to the man who gave us the framework that makes all of this comprehensible. J. Tuzo Wilson was a Canadian geophysicist. In 1966, he published a short paper that contained a question so simple and so devastating in its implications that it reorganized the way Earth scientists thought about the deep history of ocean basins and mountain ranges. The question was this: did the Atlantic Ocean close and then reopen? It sounds almost absurd at first. The Atlantic is vast. It is one of the largest ocean basins on Earth. The idea that it might have once closed, might have narrowed and shut and pressed its shores together before opening again along nearly the same line sounds like the geology of fever dreams. But Wilson followed the evidence. The evidence was in the rocks and in the fossils. Rock formations along the eastern coast of North America matched formations on the western coasts of Europe and Africa too well in too specific a way to be coincidence. Fossil assemblages that had no business being on the same side of any ocean appeared in matching sequences on opposite sides of the Atlantic. And the pattern of the Appalachians and the Caledonides, the way they aligned if you closed the ocean and pressed the continents together, pointed directly to a time when they had been one chain. Wilson's insight was that this required an older ocean, an ocean that existed before the Atlantic, that had closed during the building of the Appalachians and the Caledonides, whose closure had pressed those continents together and built those mountains, and which had then been followed by the opening of the Atlantic, the rift that pulled them apart again. The older ocean, the one that closed, is the Iapetus Ocean. The name is not arbitrary. Iapetus was, in Greek mythology, the father of Atlas, the titan who held the heavens on his shoulders, whose name was given to the Atlantic. The Iapetus Ocean is, by the logic of the name, the father of the Atlantic, the ocean that came before, that had to close before this one could open. And this gave geologists something they had been building toward without quite having the vocabulary for: a cycle. Not a simple machine, not a clock running at perfectly regular intervals, but a recognizable pattern, Ocean basins open, seafloor spreads, continents drift apart. Then somewhere, subduction begins, and the basin starts to close. The ocean narrows, eventually continents collide and mountains rise from the suture. Then the cycle begins again, rifting the new continental mass along different lines, or sometimes nearly the same lines, and an ocean opens once more. This is the Wilson cycle, named in Wilson's honor, and it is the reason that no mountain is permanent, not one, not the Himalaya, not the Appalachians in their former glory, not any range that will rise in the future. Every mountain range is an episode in a cycle that has been running since Earth had solid crust to deform. The Himalaya are in their first movements. The Appalachians have been in their final act for hundreds of millions of years. Both are passing through. Pangaea, the most recent supercontinent, the great single landmass that assembled when the collisions that built the Appalachians and the Caledonides pressed the continents into one vast body, existed as something like its full self from roughly 335 to 300 million years ago. It began to break apart around 200 million years ago. The rift that opened the Atlantic was part of that breakup. And the Wilson cycle tells us that this was not the first time such a thing had happened. Before Pangaea, there was Rodinia, a supercontinent assembled roughly a billion years ago, carrying in it the distant ancestors of rocks that now underlie the Appalachian belt. Before Rodinia, there was Columbia, sometimes called Nuna, assembled perhaps 1,800 million years ago. Supercontinents have gathered and scattered across deep time, each assembly raising mountains, each breakup beginning the erosion that wears those mountains down, each new ocean being the Iapetus of a future Atlantic. And the cycle is not done. Current models of plate motion, run forward in time, project a future supercontinent. Different researchers modeling different assumptions about which oceans close next and which rifts propagate arrive at different candidates, different geometries, different timescales. One projection produces a configuration called Pangaea Proxima or Pangaea Ultima, the Atlantic closing and the Americas pressing back into contact with Europe and Africa. Another produces Amasia, in which the Americas collide with Asia across the closing Pacific. Another, Orica, proposes yet a different geometry. The timescale in all cases is roughly 200 to 250 million years from now. 250 million years is not a number that fits easily inside a human mind, but you can approach it by remembering that 250 million years ago, the world was in the middle of the Triassic period, just after the greatest mass extinction life has ever experienced. The dinosaurs had only just begun. The Atlantic did not exist. 250 million years is the span between that world and this one, projected forward. And in that time, some ocean that we know today, perhaps the Atlantic, perhaps the Pacific, will close. And where it closes, where two continents press together, along the suture of a vanished sea, mountains will rise from what are today coastlines, from what are today perhaps gentle beaches and continental shelves sunk beneath shallow water. Those mountains do not exist yet. They have no names. No one who will ever walk among them has yet been born. But the Wilson cycle tells us they are coming, and it tells us that when they come, they will begin dying the moment the collision that built them ends. Erosion will find every crack, frost will wedge every fracture, rain will dissolve every exposed mineral, rivers will carry every loosened grain toward the sea. And slowly, over hundreds of millions of years, those future mountains will become what the Appalachians are now, and then they will become what the Canadian Shield is now, the Canadian Shield. There is no more eloquent monument to what time does to mountains than the Canadian Shield. It covers more than half of Canada. It is an enormous expanse of ancient, flat, worn rock, the exposed core of a continental mass, the bedrock of a land that has been scraped and worn and stripped by erosion so thoroughly that what you see at the surface is rock, that formed deep underground, rock that was once buried beneath mountain ranges as tall as anything the world has known, but whose mountains are now entirely gone, not eroded to stumps, not worn to gentle hills, gone. The topography is gone. What remains is the root, the deep crustal basement, the material that once lay tens of kilometres below the surface of ranges that no longer cast any shadow and have left no skyline. The Baltic Shield across the Atlantic in Fennoscandia, Finland and Sweden, and the surrounding region tells the same story. The Precambrian rocks there are among the oldest on Earth, and the mountains that once stood above them, mountains from orogenies measured in billions of years rather than hundreds of millions, are gone without a trace of their former height. The land is low, the rock is ancient. The mountains are in the past so deep that they feel less like history and more like geology's equivalent of cosmological time, the early universe before the galaxies had arranged themselves into anything recognizable. These are the endpoints. These are what the Himalaya will one day be if the Wilson cycle and erosion and isostatic rebound and deep time all proceed as the record of the past gives us every reason to believe they will. Not in any time a human can picture, not in any span that connects to lived experience, but the direction is clear and it has been confirmed by every range that has ever risen and every range that has ever fallen. And the continents themselves carry the evidence. The rock of the continents is not random, it is, in a profound sense, made of mountains. The process that builds continental crust is inseparable from the process that builds and destroys mountain ranges. Magma rises through collisions, crust thickens, rocks metamorphose under pressure. And when the mountains erode, the sediment washes to the sea where it is buried, lithified, and eventually, in some future orogeny, subducted or accreted back into a new continental margin, melted and reintruded, remade. The continents are a record of all the mountains that came before. They are the accumulated memory of orogenies stretching back billions of years, the material recycled and reworked through so many cycles that to try to trace any particular atom of calcium or silicon back to its original mountain would be to try to read a book that has been torn apart and reassembled a dozen times in the wrong order. This is the quiet truth at the center of everything this story has been moving toward. There is no bedrock in the sense of something that was always there, always still, always fixed. The bedrock is also passing through. It is material that has been mountain and seafloor and buried sediment and magma and mountain again, cycling through forms on timescales so vast that the word permanent, applied to any geological feature, is simply a measure of how short a human life is. Mountains feel permanent because they outlast us by millions of years, but millions of years is nothing to the planet. The Appalachians have been dying for 300 million years, and they are still here, reduced but recognizable. Give them another 300 million, and the question of whether anything remains above the flatness is genuinely uncertain, dependent on mantle dynamics and future tectonics that no model can yet fully predict. And the Himalaya will follow. Not soon, there is no urgency in this. India is still pressing north. The uplift continues. Everest is, by some estimates, incrementally taller this year than it was last year. Its marine limestone summit pushed a little further from the seafloor, where those shells were laid down, a little further from the Tethys Ocean that no longer exists in any form except as a memory written in rock. But the monsoons that strip the southern slopes will not stop. The rivers that carry the sediment away will not stop. And the India-Eurasia collision, however long it continues, will not continue forever. Eventually, the energy driving it will dissipate, the plates will slow, the balance will tip. and what is now a standoff will become a retreat. The Himalaya will begin to lose more than they gain. The peaks will lower, slowly, by amounts invisible across a human lifetime, but real and relentless across geological time. And the isostatic rebound will extend their life as it has extended the life of the Appalachians. As the peaks are worn down, the crustal root will rise, bringing new rock to the surface, prolonging the existence of the range past what a simple subtraction of erosion from height would predict. The mountains will fight, as mountains always fight, using the buoyancy of their own crust against the wearing of the sky. But the fight, as the Appalachians demonstrate, has only one final outcome. Deep time always wins. What will be left, in the end, is what is left everywhere that mountains have been and gone. Rock. Flat or nearly flat, old, the exhumed interior of something that was once immense. The people, if there are people, who stand on whatever land occupies the position that the Himalaya now hold, many millions of years from now, may stand on rock that crystallized 20 kilometers underground, brought to the surface by the same slow unroofing that has given us those Appalachian ridges where metamorphic rock, once buried deep, is now the highest ground in sight. They may not know what they stand on, they may not feel any particular awe at the flatness, but the flatness will be the story of what was once the highest place on Earth. There is something in this that, if you let yourself sit with it quietly, becomes less like a fact about geology and more like a fact about the nature of things. Every mountain that has ever risen has eventually come down. Every ocean that has ever opened has eventually closed, or will. The supercontinents gather and scatter. The ranges rise and fall. The erosion that seems so gradual, so imperceptible in a single lifetime, is inexorable across the deep time that the planet thinks in. And through all of this, what persists is not any particular form. Not the Himalaya at their present height, not the Appalachians at their former one. What persists is the process, the cycling, the slow transfer of material from one form to another, mountain to sediment to sea floor to buried rock to magma to new mountain, again and again, in a pattern that has been running for 4 billion years and will run for billions more. The mountains, you know, are in the middle of that story, not at the beginning, not at the end. In the middle, wherever they happen to be in their particular cycle, some rising, some falling, some so far into their falling that you would not recognize them as mountains at all without knowing what to look for. And the ground you live on, the ground that feels so fixed and so final, is also in the middle. It has been other things before. It will be other things again. There is a particular quality to this understanding when it comes slowly and settles in the way that things settle when you are on the edge of sleep. That is not frightening. It is, if anything, the opposite. The impermanence of mountains is not a tragedy. A tragedy requires something being lost that should have lasted, something cut short before its time. But mountains have no time that is proper to them. They rise when the conditions for rising are met. They fall when the conditions for falling take hold. They are the surface expression of forces operating far below, on timescales that have nothing to do with human ideas of permanence or loss. What the Appalachians were, they were fully. They rose from the Alleghanian collision 300 million years ago, scraped the sky at heights we can only estimate, shed their slopes into the rivers that ran to the ancient seas, and have been gradually, isostasy slowing but never stopping the process, coming down to what they are now. What they are now is not a diminished thing. Mount Mitchell at 2,037 meters is still a mountain. The forests that cover the old range are among the most biodiverse in the temperate world, partly because the range is old, because it escaped the worst of the glaciation that scraped cleaner surfaces further north, because the slow erosion has given the soils and the organisms time to deepen into each other. The worn-down range is not a lesser thing than the sharp-edged colossus it once was. It is a different chapter of the same story. And somewhere in the rock record, in the marine sediments that were laid down in ancient basins while the Appalachians shed their heights, all of that lost mountain still exists. Not as mountain, as material. As the sediment that was carried down the rivers and deposited in the seas and is now somewhere limestone or sandstone or shale buried under younger rock, waiting for the next event that will bring it to the surface in some form we cannot predict. Nothing is lost. It is only changed. The mountains die into the land becomes the sea floor becomes the mountain again. J. Tuzo Wilson gave us the cycle's name. But the cycle itself is older than any name. It ran before there were geologists to study it, before there were continents in any form we would recognize, before the first organism had complicated the chemistry of the surface. It is the planet's deep rhythm, the way the interior heat expresses itself at the surface, the long, slow breathing of a world that has been alive in its own way for 4.5 billion years. And tonight, somewhere in the middle of that rhythm, the Himalayas are rising, a centimetre at a time, carrying their marine limestone higher into the cold air, still in the early chapters of what the Appalachians completed long ago. And the Scottish Highlands are sleeping under their weather, their ancient Caledonian roots, separated by an ocean from the roots of the same range in North Carolina, both of them wearing gently a few tens of meters every million years, in no hurry, in no distress, simply doing what old mountains do. And the Canadian shield lies flat and ancient under the northern sky, saying nothing, being the answer to the question of what comes after all of this. It is, if you can feel it the way the geology asks you to, a kind of peace. Not the peace of things having stopped, but the peace of things continuing in their proper rhythm, unhurried, untroubled by the brevity of any particular form. The mountain rises, the mountain falls, the material goes on, and in the going on there is something that outlasts every range that has ever cast a shadow. If you have found your way here to the end of this long descent into stone and time, and the night is settled around you, let the ranges rest in your mind as they rest in the world. The Appalachians worn to their gentle ridges, the Himalaya bright and cold and still becoming, the old flat shields, the memory of mountains that no one remembers now. All of it moving, all of it changing, all of it passing through on the same long cycle that has no beginning you can point to and no end you can see from here. Where in the world are you tonight? What ground is underneath you? And what was it once? And what will it be? I would genuinely like to know there are more slow stories here of the same unhurried kind for whenever you want them. But for now, the rock is old and patient beneath you, and the night is enough, and you have come as far as you need to come. Tie off here at the Wisdom Docks. The tide will wait till morning,